level of attendance, at least at the moment. The first phase of the project is due tomorrow, so hopefully people are well on their way with that. We have not posted the second phase just yet, but we will be doing that very shortly, and it'll basically be due a week from tomorrow, so once again, make sure you get going on it very quickly. The second phase will still be, let's say, more constrained in the sense of it won't be like, having to do a complete system or anything like that. We'll just be basically modifying this first phase from what you had done to actually deal with some of the multi-level kind of characteristics that we're going to talk about today. So it shouldn't be too bad in terms of, let's say, the additional complexity. But having said that, again, make sure you get started early. Because if nothing else, the third phase of the project, which is where really everything will be, let's say, much more opened up, will indeed involve a lot of different components. And so you'll need to make sure that you really get going on that well in advance. So with that, that's, I think, all the logistics kind of stuff. Any questions on either material or project or anything like that? Okay, so if not, just as kind of a brief reminder, last time we were talking about essentially different techniques to deal with the fact that the communication channel you're going to be working over essentially is almost always going to have some sort of low-pass characteristics. In fact, it may not just be low-pass. It may have these weird notches and other things that we talked about related to reflections. So the first solution we had discussed was this equalization, which was essentially trying to apply the inverse of the channel response in order to try and get back the clean digital bits on the other side. And we said that, in fact, you didn't really have to do exactly the inverse. There was some, let's say, simplifications you could make, given that you only care about a finite bandwidth, and you don't necessarily need to have exactly the same amplitude on both sides. But then we started to move on and talk about the other potential solution, which is the so-called multi-level signaling. So the idea here is very simple. It just says that before, we were essentially sending one bit with every symbol that we sent. So per unit time, which is what I mean by symbol, we're sending one bit. Well, if our channel, or from whatever other reason, for example, the FCC says you can only use a certain amount of bandwidth, is very limited, then that means that the only other way that you could basically get higher throughput would actually be to send multiple bits for every unit time. So the idea, as is sort of illustrated here in this eye diagram, would be, as an example, you could send 2 bits for every symbol, which would mean that you'd have 4 different analog levels. And then in order to decide what bits you're actually receiving, you have to decide really well which one of these 4 analog levels was actually transmitted. Now, I've shown it here as 4 analog levels, or I should say I've shown it here in the so-called example of 4PAM. In principle, there's no reason you can't extend beyond this, right? So you could do, for example, 8PAM, 16PAM, 32PAM, etc. In fact, you can even do things like 5PAM. Those are all essentially valid things to do in terms of sending more bits per symbol. By the way, when I said that you can do things like 5PAM, I believe actually Ethernet indeed uses 5PAM. And you may wonder, what in the heck does that extra level really do? It's used for some sort of error control type of coding purposes. Okay, so indeed you can do anything, not just necessarily an integer number of bits, but you can even do sort of fractional bits by changing the number of levels you're actually sending. Okay? Now, just to be sort of totally clear as to why you would do this, I want to look at a little bit more detail as to what the implications of changing between a simple, for example, 2PAM system, meaning you only send 1 bit per symbol, versus, for example, even just this 4PAM system, which, by the way, 4PAM is what we're going to be looking at in the context of this particular project for this semester. So, if we think about our original, let's say, 2PAM kind of system, oops, come on, there we go. So if we have our original 2PAM system, if we think about what the sort of voltage levels we were transmitting were, let's assume we had essentially a differential link. Okay? So let's assume that we were basically sending either plus delta V or minus delta V to indicate our sort of 1 and 0. And by the way, sometimes I'll refer to this as 1 and minus 1. You should just, minus 1 obviously is equivalent to 0. So in other words, high and low. Okay, so now, if I've got a 4PAM system, I really can't cheat in the sense of I probably have to be using the same relative or the same absolute swing that I was actually using in the transmitter in the first place. Because otherwise, if I just magically increase my swing, I could have argued, well, okay, I could have increased the swing in the 2PAM system as well. So that says that, in some senses, 2 out of the 4 levels are really defined. In other words, they should really be the same as what I was doing before in the 2PAM system. In other words, I should be sending a plus delta V and a minus delta V. So now let me ask you guys, given that I now have to pack in an additional 2 levels into this same sort of peak-to-peak range, where should I put those levels? Yeah, exactly. Turns out you really want to put them at plus delta V over 3 and minus delta V over 3. Now, by the way, why is it that you chose those particular points? And, excuse my drawing, maybe it's not perfectly indicative of the reality of the situation, but why did you choose those particular points? Yeah, exactly. So this gives you even spacing between all of those analog levels. Now, by the way, why is it very important to get even spacing between all of them? What would be bad if you had an uneven spacing? Yeah, exactly. Because you have sort of 2 fixed poles on either end, if you move the dots in the middle in either which direction away from that even spacing, it means maybe you'll help one of those things, but you'll only be hurting the other one. And at the end of the day, of course, your performance, your noise, and etc. would be limited by the one that had the smallest spacing to its neighbor. Now, why is it important to point this out? Well, let me ask you guys. So, if you guys remember, when we talked about bit error rate, we said it was all about sort of how far away that minimum level was from whatever your threshold was. Okay? So, how much smaller, let's say, margin or distance do you get in this 4-PAM system versus the 2-PAM system? In other words, if I had a certain, let's say, distance delta V here, what would it have been? What is it now in the 4-PAM system? It's delta V over 3. Okay? So, in other words, by adding 1 more bit per symbol, we now have 3x lower margin. Right? So that sounds like a pretty steep penalty, right? Because we only got basically double the data rate per symbol, or let's say double the data rate per bandwidth, but we lost 3x in the voltage margin. So now, although we sort of talked about this in the first place, you guys tell me, what are kind of the only scenarios under which you'd be willing to pay that penalty? You'd be willing to pay this 3x loss in the voltage margin just to get that 1 extra bit. Okay, you can make more money doing it. That's true, but what's the only scenario, let's say, what's the only technical scenario under which that really happens? What has to be true about sort of the situation you're working in to make it so that you really would be happy to pay this 3x margin just to get that 1x, or that 1 extra bit per symbol, meaning only a doubling in the data rate? Bandwidth. Okay, what about the bandwidth? I mean, you're absolutely correct, bandwidth, but like more specifically. Okay, so you're right that by doing this 1 extra bit per symbol for the same data rate, I only need half of the bandwidth. That's absolutely correct. But now let's think even specifically in like this context of the high-speed links I was talking about. So what does it mean that the channel has to look like in terms of the magnitude response? And this is, by the way, all of this is going to be approximate. If indeed we're trying to compare at the same data rate, you said that now I actually do have half the bandwidth. That's absolutely correct. But what does it say that the channel had better look like for it to really be a win in terms of me having to, because notice I got 3x less voltage swing, okay? Just because of the fact that I packed that extra bit in. So you're right, I have half of the bandwidth. But what does it say about sort of the behavior of the channel in order to make it that, and let's just say the comparison I want to make is that I want to make sure that in the 4-PAM scenario versus the 2-PAM scenario, that my sort of minimum height or my minimum distance is actually at least the same, if not even better. Meaning that the actual, let's say, voltage margin I get is better. What does it say about sort of the characteristics of the channel? And I don't need anything precise. I just need to know, like roughly speaking. Okay, so you said it falls off between the sort of octave that you're considering. So one example I could draw would be, let's say, something like this. right? So let's say this would be the bandwidth over 2, meaning this is the 4PAM scenario, right? And let's say this is the bandwidth in the 2PAM scenario. Okay, so that's a reasonable idea, although it turns out, like in this picture that I drew here, which is perhaps a little bit gentle, right? Even if it just falls off at all, does that mean that you still necessarily won by doing this? Or do you actually have to fall off at a certain rate to make sure you really won? Yeah, okay, so you said something like 10 dB per octave or something like this. That's roughly the sort of the zero order kind of consideration. And all you're really saying by that was that, well, if this thing fell off by more than a factor of 3 in that factor of 2 in bandwidth, then it would seem to indicate that PAM2 would actually be better. Turns out life is actually way more complicated than that because there's lots of other considerations you have to be careful of, particularly related to how you do the equalization and things like that. But let me give you the sort of extreme example that hopefully makes it obvious, right? If your channel indeed looked like this, well, okay, now it's pretty clear, right? You just can't do anything beyond that bandwidth no matter what you want to do. And so therefore, packing that extra level indeed makes sense. Now, at least in the chip-to-chip world, generally speaking, you don't have anything that really looks like this. In the wireless world, the FCC won't exactly do that, but they do something pretty close. So that's why you tend to see these multi-level things much more often in wireless than in the chip-to-chip world. But it is indeed the case that you can get some very, very steep roll-offs, even in the channel itself. But perhaps actually sometimes just you want to get a certain data rate in a given technology. And it turns out that you just can't get clocks or you can't get sort of the circuits to run fast enough to support what you would have needed to do in the so-called 2PAM scenario. Okay? And so sometimes just because of sort of the combination of the channel characteristics and or the circuit implementation, it can be easier indeed to get these multi-level signals to really work or to really give you sort of better margin than what you would have gotten by just trying to run the circuits extremely fast. Make sense to everybody? Or? Okay, so the take-home message here is that there's no, let's say, unique, or I should say, it's not always the case that multi-level is going to be better than 2PAM. It's a very, very detailed sort of trade-off point here. So I guess the take-home message I'm trying to give you is that even though we're going to be doing multi-level signaling in this project here, you should not take that as an indication that that's always the right thing to do. There's just certain aspects of the design that are stressed by doing these multi-level signaling that I'd like to focus on for this project for this semester. Okay, but so point being, really, there are scenarios where it makes sense, but don't take that as a universal truth. Any questions on this? Or? Okay, great. So now that we have that out of the way, let's sort of get into some like really practical stuff. So the first practical thing is, well, just, okay, we talked about how you'd build like a very, very simple 2PAM link, right? We looked at what the transmitter and the receiver were. Now let's think about how you do that for a 4PAM link. So let's first think about the transmitter. So let me maybe ask you guys. And by the way, I'm going to try and build like the simplest transmitter I possibly can. In other words, something very, very similar to that current mode kind of design we had in 2PAM. And again, just as a reminder, in 2PAM, the way I built the transmitter was I basically just had a differential pair that I switched based on the data and its complement. That was switching some bias current back and forth into, of course, the 50 ohm termination resistors. So I claim there's a pretty simple way to take this exact same kind of structure and extend it to actually do a 4PAM transmitter. So anybody have any thoughts on how you might do that? Yeah. Oh, okay, I see. You could have a second bit control the I bias. That's an interesting one. You could do something like that. That one's a little bit, well, okay, you could do that. That would actually work. That one's a little bit trickier than sort of the version that I'm thinking of. But that's actually a very good idea. There's a slight variation on that that will basically do the same thing. Any other ideas? Okay. Yeah, okay, great. So what you said is, well, maybe what I can actually do is just put another one in parallel. Okay, so let me draw those two 50 ohm resistors. Let me draw these as sort of the output lines. Okay, so I could have one of these And I apologize for the, let me just redraw that a little bit so it's a little bit cleaner. So I could, for example, have one of these like this, right? And then a second one down over here. Like this. Okay, and of course let's say, and remember since it's 4PAM, that means I'm sending 2 bits for every symbol. So let me just call that D0 and, for example, D1. Okay? Now there's just one other detail we have to be careful of here. You have to size them differently. So how do you size them? And let's just assume we're going to keep the same total I bias we had before. Yeah, you're right. So D1, well, whichever one is the MSB, which let's just presume it's D1, should be twice as large as the bias current of the other one. So what does that imply about the total sizing relative to I bias? In other words, how much of I bias should I put here? And how much should I put on the bottom one? Yeah, exactly. This is going to be I bias over 3. And this will be 2/3 I bias. Right? Because in order to get them to be, one to be double the size of the other, that means there's 3 sort of units in total. And so, of course, you have to split it as I've drawn here. Does this make sense to everybody? Or? Now, by the way, in case some of you have seen this stuff before, this is very much equivalent to just building a DAC, right? A digital to analog converter, where just as I add more and more bits per symbol, it's essentially making it so that I have a more and more complicated DAC. Okay? Now, there are some, let's say, additional considerations in how you'd really build this. You may not really build it directly in the so-called binary coding like this. You might do a thermometer encoding, meaning you literally have 3 of these unit elements and drive them sort of one at a time. But turns out that for something like this, only 2PAM, meaning you're just really dealing with 4PAM, where you're really dealing with only 2 bits, something like this probably will work pretty reasonably well. Yes?
So for upsetting the devices, is it enough to just increase the tail current, or do you actually want to sort of increase the device sizes so like
Okay, great question. So the question was, are the devices that are here really the same as the devices that are there in terms of size? Or would you actually upsize these devices to match the sort of current density? And indeed, if you want to do this right, these devices should be twice as large as those devices. I just didn't label the device sizes here, but basically anything I do with sort of the bias current, you should imagine happens the same to the devices themselves. Because if not, you'll be changing, V stars and et cetera, and then things really will not match the way you expect them to. Now again, this is not to claim that this by itself will work perfectly, but at least for the kind of most of the regime that we're going to be interested in, at least for this project, this will basically do good enough. Okay? So you'll see that when I hand out the second phase of the project, I'll be giving you a transmitter that very much looks exactly like this structure. And so that's why I wanted to just point out what it does here, so that you have an idea of how this thing is really operating. Make sense to everybody? Or? Okay. So now that we've got a transmitter, let's see if we can figure out how to build our receiver. And so again, just as a reminder, in the 2PAM case, we said that we had a plus delta V and we had a minus delta V. And then we had a threshold at 0. And essentially all we did was we, at least in principle, put a comparator whose threshold was exactly at that 0 to decide if the incoming bit was above or below that threshold. So now, you guys tell me, how should we build the 4PAM receiver? And again, this is, of course, in the simplest possible case. Don't worry about, any extra gain or anything like that. Yeah, you're going to have 3 comparators. Okay, so let's again just draw that to make sure it's clear. So as we said before, we have, and let me maybe draw it a little bit bigger so it's easier to draw. We had our plus delta V, our minus delta V. We said that we were going to put the other levels at plus 1/3 delta V and minus 1/3 delta V. And as you just said, we're going to have 3 comparators. So let me draw that in a slightly different color. Where are the thresholds of those comparators going to be placed? By the way, there was one of them that hopefully should be obvious or easy. So which one's that one? Yeah, okay, so you're going to have one threshold at 0. That's definitely true. There we go. The other ones will be at 2/3 and minus 2/3. All right, now notice I've now got 3 outputs, or 3 digital bits. At the end of the day, I really only wanted 2. Right, there's really only 2 sort of independent pieces of information. So how do I take these 3 outputs and convert them back to the digital bits? What do I have to do? And I don't need any logic equations or anything, just conceptually.
Thermometer to binary encoding.
Yeah, exactly. I basically take, this is what's called a thermometer encoding, because it basically says just it basically just says, as you increase the input voltage, then you'll be increasing the number of these comparators that flip from being either a 0 to being a 1. Okay? So conceptually, you could kind of say that, well, okay, if, for example, this upper level here was 1, 1, this was, let's say, 1, 0, 0, 1, 0, 0, then if I just sort of count the number of 1s coming out of these comparators, I could convert it from being this so-called thermometer representation to the binary representation. Now, it turns out there's actually some more, let's say, subtle details into how you might really do this. You might actually do what's called gray coding on here, as opposed to the sort of straight binary encoding. Basically, just to sort of avoid issues with errors on individual comparators and things like that. But again, for this project, I'm not going to worry too much about that, because we're really mostly going to be focusing on sort of the design of the core circuitry itself. I did want to just mention it so that you keep that in mind, because indeed, that can actually cause some pretty big differences in the overall performance of the final system. But what this indeed basically says is that instead of building this simple 2PAM kind of system where all we're going to try and do is set the threshold of that comparator at 0, now we're going to have one comparator whose threshold is 0, but we're going to have these other 2 whose thresholds we're going to have to set at 2/3 and at minus 2/3. So again, keep this in mind, because as you'll see maybe in about a week or so, when we really start talking about offset cancellation or just more generally how you'd set the thresholds of these very precisely, notice that in order to set these thresholds, you really have to know what the signal swing coming in is. Because if that signal swing is changing, right, then you actually have to change this threshold along with the signal swing. Turns out that may or may not be a simple thing to actually achieve. Whereas if you look at for example, in the 2PAM case, or this comparator here in the 4PAM case, well, it always just has to go to 0 threshold. And 0 is pretty easy to measure, right? You just short the inputs to the comparator, and that's quote unquote 0. Okay? So again, just keep that in mind, because as you'll see when we hand out the project, we're not only going to introduce this multi-level signaling, but you'll see that actually in the real world, you don't actually know what the swing coming into your receiver might be. It might actually vary over some range. So because of that, you're not only going to have to deal with sort of that range of variation in terms of the analog front end itself, meaning the amplifiers and etc., but you'll also have to figure out how you're going to adjust the threshold of the comparator to really line up into the right spots, given that the input signal is moving around. So, sounds complicated. Don't worry, it won't be too bad. We'll talk a lot more about it later on down the road. But as I said, just keep this in mind, because this is going to be one of the things you'll be dealing with in the project. So, any other questions on this? Or? Yes? Okay. So you said, why would you adjust the thresholds of the comparators versus adjusting the gain on the front end? They're absolutely, or they're very much equivalent. Now, the question is, of course, what ends up being cheaper or easier to do, right? So is it cheaper to move the threshold around, or is it cheaper to build the so-called variable gain circuit in front of it? And by the way, I won't make any statement about that. You guys can play around with it and decide. But it's a great question. Other questions? Or? Okay, so if not, let's go ahead and move on to our next set of lecture notes here. And as you can hopefully have guessed, given that we've been talking so much about how these comparators are going to be used in our receiver, the next topic that indeed we'll be focusing on is the design of these comparators. So hopefully you guys have all seen some of this or something similar to it at least once before, but just to make sure we're all sort of on the same page, I wanted to maybe remind you or let's say point out something that you'll see in 1 second, which is that typically the way you're going to build these comparators is usually you have some sort of front-end analog gain followed by a latch. And what I mean by a latch here is literally in the digital sense of, when the clock is high, it'll basically pass the value through in the digital, pass whatever the digital value was. And when the clock is low, it'll essentially just retain that previous digital value at the output. Okay? Now, just to again make sure we're all on the same page, let's just kind of briefly review what are some of the specs and let's say issues you might care about when you're designing these comparators. So the first one hopefully is pretty obvious. It's just how fast can you actually run this thing? In other words, what kind of frequency can you feed into this clock and still rely on the fact that the comparator will actually tell you, yes, whenever this clock transitioned, was the input high, above 0 or below 0, or really above the threshold or below the threshold. Okay, so that's a pretty obvious one. As we discussed before, any comparator design that we build, even if, let's say, from a design standpoint, it's kind of perfect, meaning there's no systematic offset, there's always going to be random offsets or offsets that vary just because of the intrinsic variations of the devices themselves. So the other thing we're really going to care about is how big is that offset actually going to be? Because as we saw before, the bigger it is, the more it sort of eats into our margins relative to our signal swings. The other thing you're really going to care about is the so-called resolution. So what I mean by this is the following. Let's say I know what that offset is, and so I put in that offset. I put a signal that's right around that offset into the comparator. What I mean by this resolution is how big do I have to make that signal in order to ensure that the comparator actually resolves the right way relative to that offset. So in other words, can I take for example, 1 millivolt signal away from the offset and say that yes, with an extremely high probability, the comparator's output will actually be correct? Now, by the way, this resolution is very largely related to the noise of the comparator. Because as with any analog circuit, there's always going to be some noise in the transistors, the devices, etc. Which means that even if you sort of put the thing right at its threshold, its output will not necessarily deterministically go one way or the other. It'll actually perhaps even randomly flip depending upon how big that noise is. And only once you put in a signal large enough compared to the noise can you really say that it, with a very high likelihood would it resolve to either be a 1 or a 0. Another issue that we probably won't get to today, but maybe next time, is the so-called hysteresis. So it turns out that almost all comparators, in one way or another, remember what their previous decisions were. So in the most common example, if, for example, in the previous cycle, your comparator decided that its output was a 1, oftentimes it's very likely that even if you switch to the input the other way on the next cycle, it will tend to want to stay to be a 1. In other words, its threshold will actually move dynamically based upon the previous history of decisions that it made. This can actually be a pretty sort of tricky issue, especially at very, very high speeds. And by the way, I should mention that, of course, many of these specs trade off with each other. Right? So as an example, if you want very, very good resolution, meaning that you can put very, very small input signals in, tends to be much harder to do that at very high clock rates. But again, we'll see sort of precisely how that happens very shortly. I should also mention, by the way, that this hysteresis, the most common form is indeed that, for example, if you decided that the output was a 1 on the previous cycle, that you want to stay to be a 1 on this cycle. Doesn't have to be that way. You can even have comparators that if they decided the output was a 1, on the next cycle, they would actually tend to try and flip the output. Yeah, question?
I actually have a question about the offset. Is the offset you're going to get sort of, what is the spec that you're given? Is that kind of like a worst case scenario? Is that like, we'll usually get this with some probability?
Okay. So the question was, how is this offset usually spec'd? We'll talk a lot more about that when we really get into what's causing the offset in the first place. But to briefly answer your question now, most of this offset, if you do a good job with the design, will be coming from random variations in the transistors. So the way we'll spec it is we'll say, well, we want a certain percentage of our chips to actually work. So for example, we'll want, let's say, to tolerate 3 sigma of the offset to actually make sure that a chip with that 3 sigma would still work. That's typically the way we'll deal with it. But as I said, I'll get into that in a lot more detail when we really talk about where the offset is coming from in the first place. It's a good question. Okay, as we'll see in the sort of example that I'll talk about in 1 second, but as you may have even already seen in your project, you'll also often care quite a bit about what the input capacitance of the comparator is. So as you saw already, again in the project, I gave you a spec on that input cap. That cap was in many ways setting how much power your amplifier had to dissipate. Well, now if I've got a lot of these comparators, you're going to care, let's say, if I have n comparators, then there's going to be n times that input cap. That very quickly could be a large number, and again, dominate the sort of power consumption of everything in front of those comparators that's driving them. Okay, there's actually several other issues that you may be worried about. Hopefully power is the very obvious one, since we're always talking about making things low power. You will also care, for example, about how much you reject common mode variations at the input. And all comparators have a very, let's say, quote-unquote, nice property, which is that when they make decisions, they tend to also throw back some charge onto the input that's driving them. So that's a so-called kickback. Again, that can actually be a pretty substantial issue if you're not careful about it, especially if you're trying to make decisions off of very, very small inputs and have to have a full digital signal, or rather really a full swing signal at the output. So just before we kind of dive into the details of how you'd really build a comparator, just as another, let's say, example of where these things would be interesting, besides just the sort of high-speed receivers that we talked about, one of the hopefully most obvious applications for these things is in something like an analog to digital converter. Because we actually talked about a second ago in the context of the receiver, very simple way to do an analog to digital conversion is just to say if I have some analog input signal spanning some range, then if I basically put a bunch of thresholds uniformly distributed along that range, then that's exactly how I would essentially do an analog to digital conversion. So indeed, and of course, if you put those thresholds there, that's implying that the comparators are telling you, are you above or below those thresholds? So one of the most common aided analog to digital converter topologies is a so-called flash converter. And this one is actually quite popular in the, let's say, the very high-speed end of the world. Because as you can kind of see, hopefully, from the picture here, all you really have to do that analog to digital converter is fire all of these comparators all at once. And essentially, as soon as they've all decided, you have your conversion done. Right? You don't have to do any further, let's say, feedback or anything like that. So again, for sort of a high-speed converter, this is a very, let's say, simple way of doing it. Because again, it really just takes that one clock cycle to make a decision. The problem, of course, is that if I want to have an n-bit converter, I need 2 to the n minus 1 comparators. Again, very much like we already saw in the 2PAM versus 4PAM scenario. So just as an example, if I want an 8-bit converter, I need 255 of these comparators. So hopefully this now makes it obvious as an example why I said the input capacitance often matters quite a bit. Because if I've really got 255 of these things all sort of stacked in parallel off of that one input node, well, now my input cap, of course, is 255 times each one of those comparators, input cap. Make sense to everybody? Or? Yes? Yeah, so this encoder here would indeed typically be a sort of thermometer to binary, but it's not necessarily just that, because particularly when you have a lot of these comparators, you may want some additional robustness to things like, for example, one comparator just having a slightly out-of-whack threshold. But to zero order, you can think of that as being a thermometer to binary encoder. Other questions on this? Or? So, just to maybe give you now a little bit more of a hint as to how we're actually going to have to build these things, let's just do a very simple design example for this comparator. And let's actually do one very similar to what you're looking at for your project. So let's say that I'm going to build a 4 gigabit per second link, which means that I want my comparator to make a decision, every 250 picoseconds. Right? I have to decide if a bit was a 1 or a 0 every 250 picoseconds. And let's be a little bit aggressive, but let's say we really want to have, as good of a very good comparator in terms of making those decisions. Let's say that we want to make sure that it can take an input signal of 1 millivolt and bring it all the way back up to the full power supply level, which in this case, let's just assume it's 1 volt, every 250 picoseconds. So, who thinks this is an easy problem? Who thinks this is really hard? Okay, good. Few people. Well, we're going to see whether or not this is hard or easy in 1 second. But let's think about, let's say, the most immediate way you might first try to actually do this. So the first thing you might say is, well, okay, we learned a lot about OTAs in this class. And in particular, we learned a lot about single-stage OTAs. Let's just go and try and build this thing out of essentially a single-stage OTA. So it doesn't matter exactly how I do it. Let's pretend it's a cascode or something like this, just for the sake of argument, so I'd have enough gain. Because as I didn't maybe explicitly mention, but as is mentioned on the slide, indeed, to get a volt of swing off of 1 millivolt input, you need a gain of 1,000, right? All right, so let's just go and say, well, fine. I'll try and do this out of a simple single-stage OTA with this kind of cascoded-like topology that I drew here. Let's just go and quickly calculate what the implications of this would be. So, as we usually do, we just used our sort of rule of thumb, and I basically say that, well, if my bit rate was, let's say, 4 gigabits per second, I'm going to make my 3 dB bandwidth 2/3 of that. Okay, so that says that my 3 dB bandwidth is going to be essentially 2/3 of 4 gigahertz, which is, I don't know, something like 3 point something, or maybe 2.6, something like that, gigahertz. All right, now I also said that I need a gain of 1,000. So by the way, there is a minor typo in your slides. There's a factor of 2 missing there. So that's why the number that you have is slightly different than the number I have here. The number I've written here is the correct one. So let's just go and calculate what the gain bandwidth implied by that would be. So again, I need 2.6 something gigahertz of bandwidth, and I need a gain of 1,000. So that means I need 2.7 terahertz gain bandwidth. So now, let me repeat the question. Who thinks that that's an easy thing to do? Who thinks that's impossible? Okay, good. Why is it impossible, at least in the technology I gave you? And with this particular design? Yeah, it's way higher than the FT of the device. So by the way, what is the sort of peak FT from your guys' devices? Oh, well, okay, so you said 2 gig, that's probably with a pretty low V star. It's a 10, yeah, okay, 200 something gigahertz is actually, I believe, much better than the technology I gave you in this class. But in this class, you could probably get maybe about 100-ish gigahertz if you really had a very high V star in the device. But clearly way the heck off from this, right? No way in heck you can get 2.7 terahertz of gain bandwidth product out of this kind of amplifier. So am I screwed, or is there some other trick I can actually play? Ah, there we go. So why is that, why is that bad? What's the alternative? Ah, okay. So what you basically said is the trick you have to play is actually to build a multi-stage amplifier, right? Now, we'll walk through this in more detail in 1 second, but the real trick to keep in mind is that by doing a multi-stage amplifier, you can indeed break this sort of single-stage limit or trade-off between gain and bandwidth. So you probably learned, back in, I don't know, EE40 or whatever that intro EE class was, that, there was always this trade-off between gain and bandwidth. Turns out we lied a little bit. Okay? The real trade-off is actually between gain, bandwidth, and delay. Okay? And what a multi-stage amplifier actually does is it allows you to introduce that third variable in order to be able to trade off or actually do much better in terms of the gain times bandwidth, or the gain bandwidth product, so to speak. Yes? Ah, okay. So you said, what's the difference between bandwidth and delay? Bandwidth means if I took a sinusoid and I fed it into my system, up to what frequency could I, or what range of frequencies could I basically make sure that the amplitude of that sinusoid is roughly constant? Delay literally means if I took a signal and I put it into my system and I watched for that signal to come out, how long did it take to come out? And believe me, those two are quite different.
I mean, so is there, I guess unless your channel is actually significantly limited to bandwidth, is there any time to
Okay. So the question was, is there any scenario where I care about either delay or bandwidth in one more than the other? Right. So I think that was basically the question. Okay. So let's think about the context of my communication link. So if I looked at that channel itself, I would actually argue that I mostly care about bandwidth and not about the delay. Because if you think about it, delay, that's just that's basically speed of light getting from point A to point B. And there's really nothing I can do about that. That's just going to be some number of nanoseconds, right? But in terms of how fast I can pump the data, meaning what speed I can send new bits in, that's really related to the bandwidth. Okay? On the other hand, if I think about, let's say, a feedback loop, in a feedback loop, I actually care a lot about the delay. Because if I have a really big delay, then basically by the time I do anything to try and correct some error I saw at the output, it's basically stale, right? That information is completely bogus. So again, it really depends on how you're using the thing to decide whether or not you care really about bandwidth versus delay. And as we'll see in 1 second, in comparators, you're mostly, well, not mostly, I should say, you are going to exploit that trade-off to actually be able to build things that would indeed hit this kind of quote-unquote gain bandwidth product. So again, just to see how that would happen, let's just imagine that we took a cascade of completely open loop amplifiers. And let's even assume that they're essentially completely identical to each other. And just for the sake of argument, let's assume that they all, like each one of these stages, has a gain of AV. So you guys tell me, by the time I exit that fourth amplifier, how much gain does my signal have? Yeah, it's AV to the fourth, right? Because second stage, I have AV squared. This thing, I have AV cubed. By the time I get out of here, I have AV to the fourth. Well, as we'll talk about in 1 second, even if I make a very simple approximation and I just do something like open circuit time constants, then if each one of these stages was identical, if I had a bandwidth of just BW in this first stage, well, to zero order, and again, this is very much an approximation, I would have like half of the bandwidth after the second stage. I would have, for example, a third of the bandwidth after the third stage. And I would have a quarter of the bandwidth after the fourth stage. But notice, if I took the product of the total gain times the total bandwidth, it's by no means constant. Right? So just to give you an example, if my gain in each stage was, let's say, 10, what's my gain at the end of it? Yeah, it's 10,000. So I've got a gain of 10,000, but I've only reduced, or rather I should say, my gain over here is, let's say, 1,000 times higher than it was right here, but I only lost 1/4 of my bandwidth. Right? So very clearly, I'm completely breaking the gain and bandwidth trade-off here. Right? I am going to pay delay for it, because it's going to take me time to get from here to there, but in terms of gain bandwidth, I've completely broken it. Okay, I've gotten way, way higher gain with actually a relatively small degradation in the bandwidth. So what I'm going to do now for kind of a few slides is just walk through a little bit of a, let's say, optimization process. And there's going to be a few questions that we're going to answer in the process of doing that. But in the simplest example, you can, or rather the simplest sort of question we might answer is, let's say indeed we want to build one of these multi-stage amplifiers out of just a cascade of these very simple, essentially identical stages. The question we can then ask ourselves is, well, in order to get a certain amount of gain, how many stages should I use? And how much gain should each one of those stages really have? Okay? So just to answer that again, to do a very sort of simple problem setup, which is essentially going to be kind of identical to what I showed on the previous page, we'll just assume that we have a cascade of these resistively loaded amplifiers, where at each stage I have an RL, and I have a load capacitance CL that's essentially just due to the input of the next stage. Okay, and I'm just going to keep repeating these over and over and over again in order to answer the question that I just laid out. Okay, so I'm not going to keep drawing this, but you can imagine this just keeps going on however long it's supposed to. So let's assume that I have n stages in total. And let's also assume that the gain of each stage is just a stage. So as we said a second ago, what would be the total gain coming out of this? Yeah, exactly. It's just a stage to the n. Okay, now, bandwidth-wise, as I said a second ago, I'm just going to assume that I'm using open circuit time constants, meaning that I'm just going to add the time constants of each one of these stages together in order to figure out what the net bandwidth through this whole cascade is. That's not to say that that's actually the correct or let's say, exact answer, but you'll see that it's not really going to change too much in terms of the optimization. So that means that if, for example, the time constant of each one of my stages, hopefully it should be clear, that's just RL times CL. Okay? And so therefore, the time constant of my whole comparator is just going to be N times RL times CL. Make sense to everybody? Or? All right. So as I said before, what I'm now going to try and do is set up an optimization problem to answer the question of, if there's a certain total amount of gain that I want to get, how many stages should I use to do it? And what should the gain of each of those stages actually be? So in order to do that, I'm just going to sort of do a couple of tricks to maybe write things in a way that will make it clear how we actually solve that problem. So as we said a second ago, the time constant of each stage is just RL times CL. So just because I want to write this in a particular, let's say, format, I'm going to do one of those standard math tricks where I just multiply and divide by the same quantity, just to be able to rearrange some terms here. So what I'm going to do is I'm going to multiply and divide this thing by GM. So I'm going to say that that's equal to GM times RL times CL divided by GM. Well, why did I do it this way? Well, because it lets me rewrite this to just say that the time constant of each stage is just equal to the gain of each stage, a stage, divided by the gain bandwidth of each stage. Right? GM over CL, that's just the gain bandwidth of each stage. Everybody agree with me so far? Okay, great. So if you agree with that, then now again, I can basically take this and use it to say what the time constant of the entire comparator would be. Which, remember, we said the time constant of the whole comparator, that was just n times the time constant of each stage. So that's just going to be n times a stage over the gain bandwidth of each stage. Now, at the end of the day, remember I said I'm interested in trying to figure out how many stages I should really be using. So what I'm going to do here is try and just get rid of one of the variables and put it sort of in terms of n. So in particular, let's say that I told you that I wanted a total gain of a total. What would the gain of each stage be as a function of that a total and n? Yeah, it's just a total to the nth root, right? So a stage is just a total to the 1 over n. Okay, so now if I put these two things together, I can then say that the time constant of my comparator is going to be n times a total to the 1 over n divided by the gain bandwidth of each stage. And by the way, the gain bandwidth of each stage, that's kind of a fixed thing. Right? I can maybe play with bias currents and things like that, but obviously to increase that just costs me power. So now hopefully you can see that I've gotten something into a form where if what I want to do is get the fastest possible amplifier I can, given this total gain, I now have an expression for the time constant of that amplifier. And so as usual in any optimization problem, if I want to make this the lowest it can possibly be, I take the derivative with respect to n and set it equal to 0. Now, before I go any further than this, does this look familiar to anybody? Sort of the math and everything that we're doing here? Okay, one person, there's another person, there's at least like one or two other people that I know it should look familiar to, but we'll see if they remember. So, how many of you guys took 141? Okay? Does that give you a hint as to what this is? So what is this? Yeah, this is the inverter chain sizing problem. Right? And notice, by the way, the math is exactly identical. Okay, because in an inverter chain, you were asking yourselves what was the optimum fan out from a capacitance standpoint. Well, guess what? Gain is the exact same thing. So don't worry if you haven't seen this before. I will write out the full set of equations. But this is exactly the same as the optimal delay digital chain sizing problem. Okay, so all the stuff you learned about that very much directly applies here too. All right, so again, just for those who have not done this before, let me just now write out a little bit of the math. So if indeed you take that derivative, what you'll end up with is that you have A total to the 1 over n divided by the gain bandwidth per stage minus n times 1 over n squared times A total to the 1 over n divided by the gain bandwidth per stage times natural log of n. Sorry, did I do natural log, of 1 over n. And that, of course, whole thing is going to be equal to 0. Okay? By the way, the math there is not super critical. I really just did take the derivative. I'm just writing it out so that you can go home and kind of double check it for yourselves after everything is, after this lecture. But again, all I did, take the derivative, set it equal to 0. So can I go forward? Everyone's done copying down? Okay, great. So if you do that, what you'll quickly find is that you end up with the following expression. Oops, there we go. What you'll basically find is that you have 1 minus 1 over n times the natural log of A total is equal to 0. And by the way, a bunch of things drop out because as you hopefully saw, the sort of, oh, that's going to crash on me. Let's see if it comes back. Nope, let's do this. There we go. Okay. Sorry about that. We can do things upside down if you guys want. Come on. There we go. Okay. I believe we were here. Yes. Okay, so all I was saying was that if you go and you sort of take that expression that I'd written a second ago, it had a bunch of common terms in them, so I just knocked them out. And they basically become that you need 1 minus 1 over n times the natural log of A total is equal to 0. And hopefully it's pretty clear that if you then basically solve that out, it tells you that the number of stages you want to use is just the natural log of A total. And again, this should be a very, very familiar result. Now, I also claim this is actually really, really good news. Because it says that if, for example, you want to multiply the gain that you had by a factor of 10, how many more stages do you need to add? 2.3 times. Right? You guys remember we talked about in the settling context, it was 2.3 tau per decade. Same thing here. It's 2.3 stages per decade of gain. Now, by the way, just to be absolutely clear, what this really implies is it basically says that the optimal gain per stage you want to use is E. Right? Because the only way you have the sort of total gain depend on the natural log, or the number of stages depend upon the natural log, is to make the stage gain be E. So again, exactly like in 141, if you had no sort of self-loading, you came up with E as the optimum. By the way, you can add self-loading and you can also end up with something more like 4 in this context too. But for now, let's just assume that there's no self-loading. Indeed, it's E. Now, the other thing I want to point out is that if we then look at the bandwidth that we have from the whole comparator, it's just going to end up being the gain bandwidth per stage divided by E, that was just the gain we had per stage, times the natural log of the total gain, which is, of course, just the number of stages. So again, notice there's by absolutely no means a linear trade-off between gain and bandwidth. All right, you can change the gain by quite a bit and only change the bandwidth by essentially the natural log. So as we said before, for example, if you wanted to up the gain by 10, you just need 2.3 more stages. And if I already had a lot of stages, that doesn't really change the bandwidth all that much. Does this make sense to everybody? Or? Yes?
So from a layout perspective, I imagine this is nice because you have a bunch of identical stages, but couldn't you in principle vary the stages and do some tricks with like spreading poles around to make the trade-off between getting bandwidth even better?
Okay, great. So the question was, I did all of this analysis assuming basically uniform stages. Couldn't you do even better by, for example, doing some tapering or some other more complicated thing with different types of stages? And perhaps even do better than this from a gain bandwidth trade-off standpoint. So before I answer exactly that question, I would actually like to point out, as I said before, when we used open circuit time constants, we were actually not being very accurate. Turns out we're actually being somewhat pessimistic. So that even if you stick with the purely uniform stages, it turns out that the bandwidth actually does not even trade off like this. It actually trades off with the square root of the natural log of the gain. So it's even less sensitive than what I'm implying here, even with purely uniform stages. Was there another question, or can I answer the earlier one? Okay. I'll answer the earlier one, and I'll come back to you. So to answer your second question, you're absolutely correct. If you allow yourself to do sort of a non-uniform design, then for any realistic scenario, you could indeed really do even better than this. Having said that, however, all of the, let's say, math or optimization you would do to understand how to do that is exactly related to this problem. Right? You'd just be introducing some additional variables along each stage, but essentially it's the exact same idea. Right? It's really telling you how do you basically go about in making those trade-offs once you have this really multi-stage amplifier. It's the exact same sort of setup we're using here, just with a few extra variables. And by the way, if you've taken 141, I claim, again, you've actually solved that problem once already. You just may not have realized it. So that whole logical effort thing was exactly solving this type of problem.
So this last equation here, do you know either gain bandwidth per stage or bandwidth? Because I thought that's sort of what we were talking about.
Oh, well, so this bandwidth that I'm quoting you here is like the optimal bandwidth you can get given a certain gain bandwidth per stage and given a certain total gain you want to hit. Right? So the trick is that this gain bandwidth per stage, and actually you can in some senses tell me, the only thing you can really do to basically change that gain bandwidth per stage is to change how much bias current you're using, or to change equivalently the sort of V star that you're using. Right? Because especially in this very simple setup where, I'll just do it here. In this very simple setup where I just have one amplifier driving the next, if I really made these all exactly the same, then essentially it's just my own GM driving essentially my own input capacitance. Right? Which, by the way, looks a lot like FT. So that would mean that the gain bandwidth I have on each stage is just very much set by whatever FT I chose for those devices in the first place. Okay, so now let's think about this in one other, let's say, aspect. So we've said that indeed I can do very, very well from the gain bandwidth standpoint, right? I can get these extremely high gains even without paying a huge penalty for it from a bandwidth standpoint. Now let's think about what I've paid to do it. So if indeed I have this sort of chain of uniform stages, right, and I'm just going to add more and more of these stages to get the gain that I eventually am going to want to hit. Well, as we said a second ago, at the end of the day, the power we're consuming is really just related to the GM that we have in each one of those stages. So if I told you that, again, there was a certain total gain that you want to get, and I told you what the GM of each one of those stages was, what's the total GM you have to spend to get that gain, if I indeed follow this sort of optimization procedure? How many stages do I need? Again, just to get some given specified total gain, A total. Yeah, exactly. So I have natural log of A total times GM. So in other words, the power that I'm spending is going up with the natural log of the total gain that I want to have. Now, it turns out I claim this is actually somewhat wasteful, because I claim I can actually do it with the same power. Now, hopefully this just should sort of mess with your heads, but believe me, you can indeed do it. So let me and I'm going to turn the question around on you guys in 1 second, and see if you can figure out how would you actually do it in the same total power. And the only other hint I'll give is that the way to do it is to basically do something that you're generally told never to do. So what do you do? How could I get essentially the same behavior in terms of the total gain, but do it without actually having any extra power? And I'll give you another hint, maybe. Oh, wow. This really likes to crash today, so this gives you guys time to think. Oh, yeah? There you go, positive feedback. Okay, now let me get this to uncrash so that, there we go. Okay. Yeah, so it's exactly positive feedback. And the idea, hopefully, will be very clear in 1 second, even upside down. Okay, so notice here, right, the way we were getting all of that extra gain was just by taking the output of this amplifier and feeding it into something that looks exactly like itself. And then we took that same amplifier, fed it back to, again, something that looks exactly like itself. So, if indeed, rather than, oh wow, that's odd. Okay, well, we'll give it one last try and then we'll move to the board if we have to. Well, just while this is doing this. So the idea is, of course, that if what you're doing is actually feeding back to yourself, or rather feeding another stage that looks like you, if I don't want to spend any extra power for it, then what I might as well do is just take my output and feed it back to me. In other words, it's exactly like doing a positive feedback loop. And if I just get this to... Oh, that's... Oh, wow. Well... That's interesting. Let's see what that's doing. Come on. Came back to life. Come on. Okay. Oh, let me just do this. Okay. Okay, good. Okay. Sorry about that. So, as we had said before, what we were really trying to get at was that if we want to not pay the power of each one of those stages repeated over and over again, which we said that was going to give us a total GM of the natural log of the total gain times the GM of each stage, well, the simple trick is to basically take each stage, or take that one first stage, and tie it into positive feedback. Okay, so again, just hopefully I managed to convince you, in the interim of all these things in terms of the computer crashing over and over again. But just in case, you can kind of think about this in terms of what happens over time if I do this kind of structure. right? So let's say that at the beginning of this thing, I just initialize it so that there is some v in sitting there. Well, if you think about it, if this thing has a certain time constant tau, then if I wait for one of those time constants, I will have gotten a gain of AV. Right? That's kind of, that tau is indicating how long did it take me to actually get that initial gain. Well, once I have that gain of AV, I then, of course, feed back to the input. And so if I wait one more time constant, I now have AV squared. Right? And in fact, if I wait even one more time constant, let's say 3 tau, now I've got AV cubed. And so on and so forth. Okay, so again, what I'm really doing by building this thing this way is I'm really just mimicking what the original design was doing, where it did indeed take 1 tau to get an AV, another tau to get AV squared, and so on and so forth. It's just that I'm doing it in a clever way so that I really only have to, I keep reusing the same GM over and over and over again. Right? Because here, for example, once this amplifier is done, it's just sitting there and burning bias current without really giving me any further gain at that time. Whereas if I do it this way, well, I'm getting to reuse my own GM to give myself more gain simply by waiting longer. Does this make sense to everybody? Or? Okay, so let's think a little bit about how you might actually build something like this. And let me just get to the right slide. Okay, so this is sort of where I, in terms of the slides, this is where you guys should be. So the way you would build something like this, at least in the simplest case, is actually, especially once you have a differential circuit, it makes things a lot easier, right? Because tying things into positive feedback when you have the differential circuit is just a matter of essentially taking a differential amplifier and tying the one output back to the input of the other one. So let's just draw how that would look. So let's say indeed I had, and I'm just going to point it in a different direction just to make it easier to draw. Right? So let's say I had this, and this is of course a pseudo-differential amplifier, but it doesn't matter. Right? So that would have been the input of one and the output. Of course the outputs are there. Well, if I want to build this positive feedback structure, I just have to take the output of one and feed it to the input of the other one. And again, for those of you guys who have taken some of the digital stuff, this is of course just like a cross-coupled inverter. Now, all I've drawn here so far is just like, it's just a kind of a cross-coupled thing, right? There's no input yet. So at least in principle, the way we could actually get an input into this thing is maybe just to add some switches like this, and then feed in a differential input. Right? Something like this. With the idea being that initially, so for example, before I have those switches on and before I sort of let everything go. And by the way, I should mention there's of course always going to be some capacitance sitting here. For example, due to the gate capacitance of the transistors. So initially what I'm just going to try and do is make it so that the voltage, or the differential voltage at least, on those capacitors is just whatever that initial differential voltage is. Okay? And then once I let go of the switches, in other words, for t greater than 0, if I want to know what's the sort of time evolution of that differential output. So you guys tell me, if I have something connected in positive feedback like this, and I tell you that there's an initial condition of VI diff, how would this circuit evolve? How would the differential output voltage evolve over time? So in other words, what would V out of t be equal to? So why VI diff over 2? And by the way, it's going to depend upon time. Yeah, it's a growing exponential, right? Now, there was a few different hand motions I saw, so we have to be careful. It is actually growing. There's no taper off, at least not in the purely linear model. Because notice, I really do have a right half plane pole here. Right? It is actually going to go off, at least in principle, to infinity. So if we just write that out, it would be whatever the initial condition is times e to the t times c over gm. Oh, I'm sorry, excuse me, times gm over c. And by the way, the GM, of course, is just the GM of those devices, and the C is just the total capacitance at that node. So by the way, this is really sort of very much mimicking what we had said a second ago was the optimum design. Because notice for every tau, right, which in this case tau is just C over GM, for every tau, we're getting another E of gain, right, which is exactly what we said when we did the quote-unquote optimization we really wanted. So again, just to be sort of totally clear, and to remind you, remember I said in the get-go what we were going to be trading off was delay rather than gain and bandwidth? So what this is basically telling you is that if you want a certain gain, and by the way, this is often called a regenerative gain, because you sort of take something small and regenerate it up to a big voltage, then it basically tells you that the time you have to wait to get a certain regenerative gain is really just natural log of however much gain you want it to get, just like we called that A total before, times the time constant of that stage. Because again, as we said, every tau, you get an E of gain. So if we want to know how long we have to wait, it's just the natural log of that total gain times the time constant. Now, by the way, even just from this, there's a few things about designing the comparators that should hopefully already be clear. So let me ask you guys a question. Where is most of that capacitance, especially in the picture that I've drawn, coming from? Like if I really was to build this circuit like this, what is really setting that capacitance there? Yes, it's just a combination of the gate and the drain capacitance of the transistors themselves. So now let me ask you guys. If you were to upsize the transistors in this amplifier, what does it do? In terms of actually anything that we care about. Okay, so you said it increases the time constant. I don't think it necessarily does that. And by the way, to be totally clear, let's assume that we leave the V star the same, and we just go and double both the bias currents and the transistor sizes. So what would happen then? So if I double the bias current and I leave the V star the same, what happens to GM? It doubles. What happens to the capacitance? It also doubles. So does anything change in terms of the regeneration time constant? Or the regeneration time, I should say? It's exactly the same. So by the way, by doing that, what did you just manage to achieve? Yeah, you just managed to burn more power and buy absolutely nothing for it. Okay, so the point of this was simply to say that it is indeed the case that in a lot of these comparator designs, you're very much limited by driving your own capacitive parasitics. What that means is that even if you go and you upsize the devices, it doesn't really buy you much. Because at the end of the day, if all you did was both double your GM and double your cap, you're not going any faster. So it's actually quite common that if you look at these designs, you have a really, really strong motivation to make those devices as small as you can. Right? Because making them any bigger, unless there's some big explicit capacitor you're driving at the output, really doesn't make you go any faster. Okay, so indeed, with most of these comparator designs, if you really want to get it basically as optimized or really as efficient as you can, you'll tend to make those devices very, very small. Now, you do have to be careful because when you make the devices small, you will have a larger input referred noise, just due to essentially KT on C. Okay? And as we'll see shortly, the input referred offsets, due to the random variations, will also be larger. But nonetheless, it tends to be sort of, you tend to indeed get pushed in the direction of making those devices really as small as you can. Simply because from a speed standpoint, upsizing typically doesn't buy you anything at all. Okay? Does this make sense to everybody? Or? All right, now, I drew this picture here, but in reality, this is maybe not, let's say, the best way of doing things. In that, notice, when I had these switches to the input, initially, obviously, this thing is going to be fighting with whatever is driving the input, and you may or may not really want to do that. So when you really try and build these comparators, you'll typically do it in a somewhat different way. You'll typically basically isolate the inputs versus this regeneration stage. So just to sort of finish up for today, let me show you the, let's say, most straightforward way of doing that, at least in the still sort of relatively analog kind of structure. And so by the way, the design that I'm going to draw for you here is actually what I'm going to give you as, let's say, the default thing to start with in your project as well. So it's worthwhile understanding sort of how this thing is going to work. So the basic idea is very simple. So as we said a second ago, in order to get that sort of, let's say, regeneration behavior, what I really wanted was some kind of cross-coupled pair. So indeed, I'm going to have that in this design as well. But what I also need is a way of kind of initializing the voltage going into that cross-coupled pair. So in the so-called CML comparator, or the CML really, it's a latch. And by the way, CML just stands for current mode logic. The way you're actually typically going to initialize that voltage is to basically have the thing operate in two different clock phases. Okay? So in the first clock phase, what you'll actually do is essentially just take the input signal. So let's say this is VI plus, VI minus. You feed it just into a normal differential pair, okay, driving, for example, a resistive load. And then what you do is in the other clock phase, in other words, when you actually want to make the decision, you then take the output of that original differential pair and essentially connect it to that cross-coupled pair right here. Okay, and by the way, of course, the outputs are here. And let me just be sure I get that right. This is going to be V out minus and V out plus. Okay? So again, the idea is very simple. In the first clock phase, in other words, when clock is low, I have no current flowing through this cross-coupled thing. So it's basically not doing anything. And I just have essentially a normal differential amplifier. Then what I do is when the clock goes high, I shut off this current right here, which basically means that this input pair turns off. And I turn on this cross-coupled pair here, so that once this is really on, it just takes whatever the initial voltage was and tries to regenerate it all the way to one side or to the other. Make sense to everybody? Or? Now, just to be totally clear, in this kind of design, if I say that my output is a 1, what's the kind of, let's say, what's the single-ended output that I would see on, for example, either V out plus or V out minus? So let's say that V out plus is a 1. What would you say? What would be the single-ended voltage associated with that? Yeah, it'd be VDD. Okay? And if that same side was a 0, and let me just be totally clear, what would that output be? Yeah, exactly. It would just be VDD minus I bias times R. Because even though, as we said, over here, we said that we would have sort of this thing just going up exponentially. Obviously, eventually, what will happen is you just take the full bias current and steer it to one side or to the other. And so once it's steered to that one side, this is indeed the output voltage that you would get. So as I said, this is kind of the, let's say, simple, or simplest first order way of building these kinds of comparators. And as I said, this is what I'll be giving you in your project. But there are, let's say, some practical annoyances with really using these things. One is, as we just pointed out, this is really acting like a comparator. It is giving you a quote-unquote digital output signal. But that signal is not swinging all the way from 0 to VDD. Right? It's only from whatever VDD minus I bias times R is up to VDD. So oftentimes, at the end of the day, you will have to take some additional circuit afterwards to basically take this low swing digital signal and translate it back up to let's say, the full 0 to VDD types of swings that the rest of the system might be interested in. But by the way, for us, at least for now, for the project, don't worry too much about that. It is indeed okay for you to use this kind of swing, as long as, of course, it's not ridiculously small. And again, we'll give you some specs on that down the road. But do keep that in mind, because in most real or practical systems, you will indeed have to take this kind of signal here and get it back to the full 0 to VDD kind of swing at the end of the day. So any questions on this? Or? All right, if not, we'll pick up next time and we'll actually show you some more comparators that actually give you that full 0 to VDD of